Have you ever looked up at the night sky, at that vast sea of stars, and wondered, are we alone? It's a question that has captivated humanity for centuries. For most of our history, we could only speculate. But today, we are living in a golden age of discovery. We're not just looking at stars anymore. We're finding entire worlds orbiting them. These are exoplanets, and they are completely rewriting our understanding of the cosmos. So, let's start with the big number. How many exoplanets have we found? As of today, astronomers have confirmed over 5,000 exoplanets. That's 5,000 worlds beyond our own solar system. And that number is climbing every single day. Think about it. Just a few decades ago, we didn't know for sure if any other stars had planets. Now, we know that planets are incredibly common. In fact, it seems like most stars in our galaxy probably host at least one planet. These alien worlds aren't just clustered in one small patch of the sky. They are scattered throughout our Milky Way galaxy. Some are relatively close, just a few light years away, while others are thousands of light years distant. We've found planets orbiting stars like our Sun, stars much smaller and cooler called red dwarfs, and even giant, hot blue stars. We've even found planets orbiting two stars at once, like the fictional planet Tatooine from Star Wars. The diversity is simply mind-boggling. So, what are these worlds like? Well, they come in all shapes and sizes. We've found hot Jupiters, which are giant gas planets, bigger than our own Jupiter, but orbiting so close to their star that their atmospheres are scorching hot, with temperatures reaching thousands of degrees. Imagine a year on one of these planets lasting just a few Earth days. Then there are the super-Earths. These are rocky planets, like our own, but bigger and more massive. We don't have anything like them in our solar system, so they are a complete mystery. Could they have continents and oceans? Could they have atmospheres? These are some of the most exciting targets in the search for life. We've also found Mini-Neptunes, which are smaller than our Neptune but larger than Earth, likely with thick, gassy atmospheres. And of course, there's the ultimate prize, Earth-like planets, worlds that are roughly the same size as Earth, made of rock, and orbiting their star in the habitable zone. This is the region where temperatures are just right for liquid water to exist on the surface. Liquid water, as we know it, is a key ingredient for life. And yes, we have found several of these potentially habitable worlds. Planets like Proxima Centauri b, orbiting the closest star to our Sun, and the TRAPPIST-1 system, which has a whopping 7 rocky planets, several of which could have water. But how do we find these distant worlds? We can't just point a telescope and take a picture. They are incredibly small and faint, completely lost in the glare of their parent star. It's like trying to spot a firefly next to a giant searchlight from miles away. So, astronomers had to get creative. One of the earliest successful methods is called the radial velocity method, or the wobble method. Imagine walking a big, energetic dog on a leash. As the dog pulls and runs around you, you get pulled and wobbled a little bit too. The same thing happens with a star and its planet. As a planet orbits its star, its gravity tugs on the star, causing it to wobble ever so slightly. Astronomers can detect this wobble by looking at the star's light. As the star wobbles towards us, its light waves get compressed, shifting towards the blue end of the spectrum. When it wobbles away, the light waves get stretched, shifting towards the red. This is the Doppler effect, the same thing that makes a siren's pitch change as it passes you. By measuring this tiny shift in the star's light, we can deduce that a planet must be there, and even estimate its mass. This method was brilliant, but it had its limitations. It's best at finding very massive planets that are close to their star, because they cause the biggest wobble. It's much harder to find smaller, Earth-sized planets that are farther out. Then came the transit method, which has been a total game-changer, largely thanks to missions like NASA's Kepler Space Telescope. Imagine you're watching a bright light bulb from a distance. If a tiny moth flies in front of it, you'll see the light dim just a little bit for a moment. The transit method works the exact same way. We stare at a star and measure its brightness very, very precisely. If a planet's orbit happens to be aligned just right, from our point of view, it will pass in front of its star. This event is called a transit. When the transit happens, the planet blocks a tiny fraction of the star's light, causing a small temporary dip in its brightness. By observing these regular dips, we can confirm the presence of a planet. We can figure out how long its year is by timing how often the dips occur. And by measuring how much the light dims, we can calculate the size of the planet. This method has been incredibly successful, responsible for discovering thousands of exoplanets. The downside: it only works for planets whose orbits are perfectly aligned with our line of sight. For every system we see transiting, there are dozens more that we miss, simply because their orbits are tilted. So, you can see why these early discoveries, as amazing as they are, were really just the tip of the iceberg. The wobble method found the big, heavy planets. The transit method found the ones that happened to be perfectly aligned. Both of these techniques have a built-in bias. They gave us our first glimpse into the planetary census, but it was a biased glimpse. It's like trying to understand all the fish in the ocean by only using a net with very large holes. You'd catch all the sharks and tuna, but you'd completely miss all the smaller fish. You might conclude that the ocean is mostly full of giant fish, but you'd be wrong. That's what was happening in the early days of exoplanet hunting. We found a lot of hot Jupiters, which led some to believe they were the most common type of planet. But now we know that's not true. They were just the easiest to find with our early tools. The reality is that for every planet we've found, there are countless others we can't see yet. Worlds that are too small, too far from their star, or whose orbits aren't aligned for a transit. The 5,000 confirmed planets are just a tiny sample from a very small patch of our galactic neighborhood. The Milky Way galaxy has hundreds of billions of stars. If most of them have planets, then we are talking about trillions of worlds out there. Trillions. The discoveries we've made so far have confirmed that planets are not rare. They are the rule, not the exception. The universe is teeming with them. And this is just the beginning. We're now moving into a new era of exploration with incredibly powerful new instruments, like the James Webb Space Telescope. We're no longer just detecting these worlds, we're starting to characterize them. We can analyze the starlight that passes through a planet's atmosphere to figure out what gases are present. We're looking for signs of water, methane, oxygen, the chemical fingerprints of a living world. The secrets hidden beyond Earth are slowly being revealed. Each new discovery brings us one step closer to answering that profound question: are we alone? We don't have the answer yet, but for the first time in history, it feels like it's within our reach. What we have found so far is just a tantalizing preview of the cosmic wonders that are still waiting to be discovered. Thank you so much for joining me on this journey beyond our solar system. If you enjoyed this cosmic adventure, don't forget to like, subscribe, and hit that notification bell so you don't miss our next video. See you in the next one.